and welcome to my presentation about extremophiles. I will be presenting you the paper from Ian von Hegner with its title Extreme Exoworlds and the Extremophile Paradox. My name is Filip Trendafilov, and I'm an informatic major with 150 credits and 30 credits minor in astronomy and astrobiology. My title of the presentation is Extremophiles and the Cutting Edge Framework that has been created in the paper. So why did I pick this topic? For one, I'm very surprised about the vastness of the universe, about all the topics that I've learned during my courses in the minor. And I just can't really believe that us humans are the only living organisms in the whole universe. I'd like to believe that there are more organisms, and with the research about extremophiles, they might give us insight on further informations on how life could develop, why or what are tricks that extremophiles are using to survive on extreme conditions, like on Earth and in the deserts or in super cold regions. This could then help us further research for extraterrestrial life and help us out in that case. Right. Coming to the outline, I'll give you a short introduction about the extremophiles. Then we'll look at the paper introduction. Then we'll go and have a look at the main part of the paper, which will be the extremophile paradox, the uninhibited yet habitable world section, chemosignatures, which is basically a subsection of the uninhibited yet habitable worlds. Then we'll have a look at different variants and conclude the presentation with the conclusion and some personal notes. I'd like to start the introduction with naming different categories that we've looked at in the introduction to astrobiology course. So for one, we have the thermophiles that thrive in high temperatures. Then we have the cryophiles that live in extreme cold environments. We have xerophiles that can exist in almost waterless conditions, barophiles that can withstand extreme gas or liquids pressures, acidophiles, they thrive in acidic environment, so low pH. Alkaliphiles, they thrive in alkaline environment. Holophiles can exist in very salty environment, and radiophiles, which exist within levels of ionizing radiation. So coming to the paper introduction. Extremophiles are organisms that are tolerant to environment extremes, and they have evolved to grow optimally under one or more extreme conditions. They've gained in prominence in the research by providing an experimental approach and valuable data, but also analogs to potential extraterrestrial life. It also shows capabilities in the ecological range of life's possibilities, which was not known to be that high before the existence became known of these extremophiles. For example, we have the cryophiles, the Dinocus geothermalis, which is capable of surviving temperatures up to -25 degrees Celsius, or the Planocus halocryophilos oral, capable of growing at -15 degrees Celsius with 18% of salinity. These insights are important because not far from our Earth, for example, on Jupiter's moon Europa and Saturn's moon Enceladus, they both possess liquid suboceans beneath their ice shells and could help us further investigate extraterrestrial life in these locations. Then we have the thermophiles, which are, for example, Geogemma barossi 121. It's an organism capable of living at temperatures up to 130 degrees Celsius. This is important in the case where, or is relevant, as it was estimated that hydrothermal vents activities at temperature greater than 90 degrees Celsius may exist on the seafloor of Enceladus. Continuing with the xerophiles, we have, for example, the Crococidiopsis, which can endure several dry wet cycles and survive prolonged periods in arid hot deserts. This becomes relevant when looking for extraterrestrial life at worlds or moons similar to Mars. Now I would like to tell you more about the goals of this paper, of this study. Namely, Ian tried to create a framework of high-level characterizations of the evolutionary mechanisms taking place, such that analysis of example scenarios can provide predictions of what could happen in certain situations. These insights, then again, can provide scenario abstractions and characterizations that tell what must necessarily restrict or promote extremophiles, and therefore their presence on solar system bodies and maybe even rogue planets when evolutionary mechanisms and processes are included. These scenario abstractions and characterizations tells us what must apply to emergence or continuations of extremophiles in a world and their making. Evolutionary theory will be used as a framework to characterize example scenarios, but no specific extremophiles will be used to provide this framework. Further, then we'll have a look at the explanation of chemical evolution, the biological evolution, and the determinism and non-determinism. Heading right into the first big section of the paper, the extremophile paradox. On this image, you can see three different sections. The first section, the A section, you can see on the bottom part that the organism is able to sustain in a relaxed environment. After adaptation and evolution, it can also live in semi-extreme environment. And then on the top one, you can see the organism being adapted to extreme environment. In the B section, you can see that there can no organism, namely the mesophiles, can exist in an extreme environment. Whereas in section C, you can see that the extremophiles are able to sustain themselves in extreme environments. We'll need that later on. So what is the paradox about? So we've heard that extremophiles' habitat is in extreme environments, but their ancestors of extremophiles, so the mesophiles, could not live in that same habitat. So for the first life form must have required relaxed environment, right? Well, we can easily try and explain that in a mathematical manner. For example, let's set up the four variables P, Q, R, and S. P being the extreme environment. Q, a mesophile can emerge. R, a mesophile can evolve to become an extremophile. And S, there are extremophiles in that environment. So reading the first sentence, if P, then not Q. So if there's extreme environment, there cannot be a mesophile, or a mesophile cannot emerge. In the next sentence, we have if not Q, so if there cannot emerge a mesophile, it can't be an extreme environment. In the next sentence, last sentence, we have if not R, then not S. So meaning if it's not an extreme environment, there are no extremophiles in this environment, leading to the conclusion that if P, then not S. So if the extreme environment is in fact extreme, there cannot be extremophiles in this environment, which is a bit of a paradox, right? So the paradox, as extremophiles evidently do exist in extreme environments, and as ancestors originated in relaxed environment, the range of emergence possibility is equally restricted. So those were the paradoxes presented in the paper. And now we're moving forward with the uninhabited yet habitable worlds section. They infer that the chemical evolution is possible, but those worlds are still uninhabited. So what's the twist here? Let's say if the chemistry is favorable and there are energy sources present, the conditions for chemical evolution is present as well. But there's no native life on the world with conditions for chemical evolution that may indicate that chemical evolution is not deterministic, but includes contingent events as well. This is the case for biological evolution. And if biological evolution and extremophile can live to become the progenitor of biota, then conditions for chemical evolutions are also present. With extreme environment giving, there might be imported organisms and also chemical evolution possible, but no native life, other life than extremophiles. In this part, we will be talking about chemosignatures. In this scenario, we're talking about imported organisms. So organisms that might have been planted intentionally, or come from other celestial objects, crashed onto some stellar body and therefore landed there. In this graphic, we can see 5 different sections, or 4 different sections, namely A, B, C, and D. So in A, we see that there is on the side, there's a chemical evolution from left to right, and everything is in an extreme environment. In A, that's very well possible. So there is chemical evolution in both of them. In B, with the biological evolution, it's not possible. Here we have again on the bottom, there's the ancestor cell, and on the top we have the adapted cell, the extremophile. So there cannot be an ancestor mesophilic cell surviving in an extreme condition and is therefore also not able for biological evolution. In C, we have an extremophile that is very well able to live in the extreme environment, and in D, we have an imported organism that just aligns with the interest of the extreme environment and its own survivability. When we're talking about chemosignatures, it's almost analog to biosignature, but we're not looking for signs of life in a world, but for the signs of whether chemical evolution can occur on a world or not. Conjecture that if chemistry favorable for life is present and energy sources accessible for life is also present, then we have the conditions met for chemical evolutions. Such organisms undergo an exponential growth and fill all available niches in a world. For example, if we're talking about how long it would take to colonize Europe, so that's Jupiter's moon, it would suffice to have 122 cell divisions, which is absolutely crazy. From there on, we can get more exotic biosignatures as life is escaping worlds, but it would need immense force. For example, that could happen on Enceladus, which have been observed to emit jets of mainly water from its southern polar region. Where does all this water go? And if there is life in this water, maybe Saturn has aggregated these biobanks on its rings. Now, heading to the different variants the study has presented, we can have a look at the environment, at the scenario with an environment that is, for example, always extreme. Well, for one, we can say there cannot be life, or at least maybe non-native life could exist. But what about the intermediate step from chemical evolution to extremophile? Well, it still might happen, but it is still very improbable. further investigate that, we'll set two rules. So in the first rule, the series of layers are overcome with an increase in the extremity of the environment stressors. But before the emergence of first functional cells, before biological evolution begins, there are a number of layers with quasi-biotic steps where assembly of a cell occurs, namely the chemical evolution. So here are the intermediate steps. In the second rule, the first autonomous cell is not a Platonic absolute, but it's just a variant. Biological evolution addresses individual variation and natural selection. Variation does not necessarily begin with the first functional cell. So the pregenote designates pre-cells preceding the sen ancestors, meaning may have also been variants among the pre-cells that came before the first functional cell. Therefore, the first autonomous cell on one world will be the simplest possible organism, but still able to experience modest variations compared to the first autonomous cell on another world. They will be almost identical, but modest space for variation between them. By extending the Darwinian principle, so it's meaning no specific species occupies a privileged position in nature, then there's also nothing privileged regarding even the first autonomous cell on Earth. With these two abstractions in mind, a series of layers where quasi-biotic steps occur and the first autonomous cell occurs as a variant, evolution can occur from extremotolerant organisms to extremophiles, in contrast to previous scenario, where evolution occurred from mesophiles to extremophiles with no intermediate steps. We can set the hypothesis. So significant but possible deviation is possible, where a cell on the border to a progenode and autonomous cell achieves extremotolerant capacity. An organism that makes a single leap without intermediate steps, adaptations, and happens to be viable in specific environments, called saltational event. These events have been discussed mostly unfavorable, but have been supported in individual cases. Chemical evolution requires some sub-processes that are delicate and will be destroyed in extreme environments, structures like RNA or DNA. Coming to yet another scenario. Let's say that new scenario, in many of the layers, the environment and the layers in the chemical evolution can occur under extreme conditions, and only in the last layer of chemical evolution, the cell is destroyed. Argumentation. As in the last scenario, if chemical evolution is possible on a solar system body, then the possibility of this phase must necessarily be present as well. These environmental stressors destroy the simplest functional cell that arises as an end product of chemical evolution. Let's set up two assumptions so we can further investigate this scenario. Assumption 1. Many progenode variants can occur simultaneously in extreme environments, and instead of all variants being destroyed in the last layer, there is a possibility that one variant achieves an extremotolerance. Assumption 2. Evolutionary conditions remain, but split into different components, such that the chemical evolution can occur with certain combinations. Extreme conditions vary in extremity, but also there can be different extremes simultaneous. A cell on border between a progenode and an autonomous cell achieves extremotolerance depends on two things. So we have the combination of components of a cell. Let's set that to n, the number of components 56, and the different extreme environments. So each stressor gets a number, and let's set that number to k equals 6. And we want to get an alignment of interests between the cell components combination and the extreme environment composition. To try and make this conclusion a bit more clear, we can try and set a real-world example. For example, let's say that the cell combination of components is a lock with its set of obstructions, and the environment, its combinations of components, is the key with its notches or slots. Then a match means that the cell can withstand the environment with its stressors, allowing the cell to survive and even reproduce, even if it's an extremophile. So in the last phase, the cell must achieve a random composition with precise combination that is a fit with the surrounding environment. It's not natural selection, but it's almost like a very improbable, fine-tuned match to exactly match the environment conditions. What is the probability of a chemical evolution in a single leap? Well, the progenitor variant to obtain extremotolerant, it has to match 6 numbers of components from the environment with numbers of its own pool of 56. So the probability would be 1 in 32 million if no permutation, so no order, is regarded. If we now take the order also into account, we end up with odds of 1 in 23 billion. So maybe for the comparison of the Milky Way galaxy, which has 100 to 400 billion stars, and therefore more planets, moons, then odds are in our favor. But we haven't taken into account that maybe only a very small part of these 1 to 400 billion stars would make an habitable environment such as similar to our solar system. So maybe a little critique here. So very few components were used for the cell, so only 56. So taking more realistic components numbers and more environmental variables would lead to distinctly lower odds. Maybe if taken into perspective with the local group, we might get, then again, comparable results. Coming to the conclusion of this paper, of its own conclusion. So the study tried to create a framework to aid and simplify the astrobiology goal of understanding the fundamental conditions that underlie the origin of life and evolution. The objectives taken into account here were the chemical evolution and biological evolution and the conditions with which they occur. The distinction between the universal necessary features of all life and features that have merely arisen due to historical circumstances and due to terrestrial life being the only life form we know, this supports this distinction. The extremophile paradox shows an evolutionary mechanism that must be universally applicable, allowing the place restrictions and search criteria for life elsewhere in the galaxy. The conditions of having a near star energy source environment that is favorable is only secondary, since if the solar body is in itself unfavorable, it would also not have evolved over time to allow extremophiles to occur. So the primary criterion is distinguishing between worlds possessing relaxed or extreme environments. Another objective of astrobiology is the examination of whether a world possesses conditions for life by constructing a scenario it allows to analyze and limit the restrictions that apply to the chemical evolution and biological evolution. This, again, helps us refine the understanding of origin of life. It makes it easier to choose a direction between so many different paths that we can head and research into it, but setting these limitations, these restrictions, we can predict and already cut out paths and better just choose a path that seems promising. Critic might say that the important organisms is a planned action, so it's not really valid. Well, what about the heavy bombardment era? Such a global impactor could erase all life on the object, but might send parts into space. So 2 paths open again. You have organisms on the object that's been flying out of its host. It might come back, but then again, 2 different paths open. Maybe the impact was so big that the host has changed its whole environment and the organisms that land again cannot survive. Or the organism lands and it can start over where it stopped. On the previous path, maybe it doesn't even come back to the host. Maybe it just flies around and hits another object. And then again, either the next host planet has habitable environment or it doesn't. With that, I'm concluding the review of this paper. and I would like to give you some personal notes. So coming to my personal notes, I would like to share some thoughts. So I didn't really understand why there were no specific extremophiles used in this analysis. It would have helped me for sure a lot if there was some actual specific examples, because this whole paper was very, very theoretical, and there was lots of conceptual, high-level, abstract thinking, abstract reading. Also, then with the extremophile paradox, I mean, extremophiles thrive under extreme conditions, but we're not the origin. Wasn't early Earth in an extreme condition itself, and we can date back the first organisms more than 4 billion years ago? Then again, maybe finding an exoplanet with conditions met such that extremophiles could live on, but deducing that there are no extremophiles because of the argumentation on page 4, where it was stated, due to the very conditions evolution operates under. But knowing that this planet was existing millions or billions years ago, it might have developed similar to that of ours. What improvements would I like to see? A flowchart would have been amazing, or a decision tree. Basically, it's both the same, but having those paths visualized would have helped a lot to understand also the written part of the study. So coming to the future outlook, the analysis of scenarios for life and its conditions could provide conceptual framework and conceptual tools for future focused structured observations and analysis for astrobiology. It also provides checklists, and you could draw flow diagrams for conditions or paths that can be investigated and researched, as just said before. And I think it's a good starter to grasp the complexity of extraterrestrial life and the research importance of extremophiles on our Earth itself. I think this could really, really help us with finding native life. Thank you for listening. And on my last slide, I have stated all the different papers and sources that I've been using. And the first one being my main paper from Ian Den Hagen. Thank you so much for listening, and see you in the comment section of YouTube.